In this lecture, we're going to be continuing our discussion about some of the topics in Unit 3, particularly formal issues in architecture, and drawing a lot of this subject matter from Chapter 7 in Form, Space, and Order. And here we're talking about ordering principles. So a lot of these ordering principles can be seen in architecture, and it can be seen in individual buildings, or in some cases it can be in a city or an urban planning context, or it could be a cluster or grouping of buildings. But you see these ordering principles play out in various ways. And you could take a particular building and you might see many ordering principles within that building. You might see one very strongly designed or occurring in that building, but you'll start to hopefully view buildings a different way once you look at them through the lens of some of these ordering principles. One of the first ones that we talk about is the axis, or the idea of creating an axis within architecture. Now, an axis exists outside of architecture. You basically have a line that's established by 2 points occurring in space. This is a very common geometric tool or function. But when we're talking about an axis, it could be a line around which other objects are placed. It could be a line that goes through other objects. It could be a blank space or a void space inside of a building or a complex of buildings. In this example, we're going to look at the axis as an ordering form around which other objects are placed. So here we're looking at a plan view of Teotihuacan, and this is the archaeological zone, Teotihuacan, outside of Mexico City. And Teotihuacan was an ancient civilization and was in the pre-Columbian era, so a Mesoamerican civilization that predated the Aztecs. Now eventually the Aztecs inhabited this area and actually gave it the name Teotihuacan. But so some people tend to think that the Aztecs were the originators or the builders of this complex, but that civilization predates the Aztecs. Now, there's a lot of debate about who built this complex, and it's some people think it was the Toltec civilization, but some of the buildings predate the Toltecs, so we know that it was a large society and a large civilization that occupied this site. And as we're looking at this, you see this strong line running, kind of left to right on the screen. And this is a major axis that serves as a passageway or a road that is like the main avenue through the civilization. And actually the name that it's given is Avenue of the Dead. So the Avenue of the Dead is really the unifying element that goes throughout this site. Now, at its peak of population, it's estimated that there were over 120 or 125,000 people living at this site, and that made it, for the time, around 100 BC, it made it the 6th largest population in the world. Now, Teotihuacan was established around 100 BC, but was inhabited continually until around the 8th century AD. Now, when we look at the buildings that are still remaining, it doesn't really address everything that was here at the time that there were that many people living there. It was a pretty sophisticated society architecturally because there were basically apartment complexes or multifamily houses that held a lot of people in a pretty dense area. Now what we see here is what is remaining. and the main complex buildings are both pyramids and religious or ritualistic buildings. And so this Avenue of the Dead that we see running all the way through has some major elements on either side of it, and then probably its most major element at the very end that you see kind of on the left-hand side of the screen. We'll take a look at that. When you have an axis that's serving as an ordering principle, like at Teotihuacan, the axis is defining or is defined as a major element in this city. So when we have an axis, sometimes the ends of the line of the axis are open, or there's nothing there, and we're just looking at the axis to serve as an ordering principle with parts of a building or other elements on either side of the line of the axis. But sometimes, since the line of the axis is defined by 2 points, kind of 2 points in space that are defined and then that line in between, sometimes those end points of the axis are actual built items, or they're what we would refer to as terminating elements. So when we look at the Avenue of the Dead at Teotihuacan, on one end there's a major terminating element that we see here, and that is the Pyramid of the Sun. The Pyramid of the Sun serves as the terminating element on one end. There is not a corresponding element on the other end of the axis that serves the same purpose. Now, interestingly, there is another major pyramid along the Avenue of the Dead, which is the Pyramid of the Moon, which we'll see in the next slide, but they're not, symmetrical about the axis. But this is a great example of a terminating element. You see this occurring over and over in architecture, and you also see it over and over in city planning, urban planning, town planning. The axis can serve as either a thoroughfare or a visual axis or a visual corridor. You see this in Austin. If you're in South Austin and you're looking up Congress Avenue to the north, that avenue serves as an axis, and the Texas Capitol building is the terminating element visually of that axis. Now, Congress Avenue kind of goes through that and continues on beyond the Capitol, but plan-wise and visually, you're seeing that as a major terminating element. So you don't have to have terminating elements on both ends of the axis. Now, sometimes that occurs where you have 2 definite terminating elements on either end of a strong linear axis. In Washington, D.C., on the National Mall, the mall itself serves as an open corridor and a strong visual connecting axis, a physical axis, and unifying element for the whole mall. So there are things along the axis, but on the 2 ends there are definite terminating elements. So on one end is the U.S. Capitol building, and on the other end is the Lincoln Memorial. So you can look up one end of the axis, look up the other end, and you can visually and physically see those terminating elements. Here at Teotihuacan, you're seeing it, visually. The avenue is quite wide. It's not as wide as the base of the Pyramid of the Sun. You can see this is just massive, especially when compared to people walking around it and up on it. But it definitely serves as a visual unifying element, and the axis, we can also imagine, was the center of city life at Teotihuacan. For that many people to be living in a small area was a pretty unusual thing in that era. So, in the 1st century BC, most civilizations would have been agrarian or rural types of settlements or civilizations, and this acted as a city center of a much larger area. Now, when we look at terminating elements as being important, in the overall structure of the complex or the structure of the building. They might have certain symbolism, and just by its use as a terminating element, it almost elevates its importance in the layout of the entire structure of the entire complex. So you can imagine architecturally, if you're inside of a building and you see a long corridor and you are walking down the corridor, or even if you're just looking down it, whatever is placed at the end of the corridor that you're walking toward and you're seeing continually the entire time you're walking down the corridor, whether or not the designer or whoever owns it or constructed it meant for that to happen, that terminating element becomes more important because you're seeing it isolated at the end of this axis. So even if you have other things on either side of it, if you had things on either side of the corridor, psychologically you're not going to perceive that as being as important as the terminating element that is at the end of that corridor. So we can see that in this example of the Pyramid of the Sun at Teotihuacan. This is a view from the Pyramid of the Sun once you're up a couple of levels, having gone up the steps, when you're looking back down the Avenue of the Dead. So you can see there is not a corresponding terminating element on the other side of this axis, but off to the left you see the Pyramid of the Moon that is along the axis. So it's kind of curious that that's where it's placed. There is not necessarily bilateral symmetry or symmetry running down the axis and then having a mirrored representation of the other pyramid on the other side. But because of the great size and scale of these pyramids, they definitely held importance within the cityscape. And the Pyramid of the Moon is slightly smaller than the Pyramid of the Sun. Not quite as tall, but that kind of makes sense in the hierarchy of the buildings, that the one that is the terminating element would be slightly larger and more grand in scale. Now, as we look at this, visually it's fairly interesting to see the backdrop of the mountains surrounding this valley right behind these large pyramids. So, some people theorize that these were meant to reflect the surrounding mountains and had symbolic importance. There's a lot of speculation about what happened at these sites. There are some very well preserved murals at some of the buildings at Teotihuacan, so we can get an idea of some of what daily life must have been like here. And it seems to have been a fairly sophisticated civilization because of the number of people that lived here. There were over 100,000 people that lived at Teotihuacan, so you can imagine that having that many people in this area and functioning as a society for several centuries would have been quite a feat and quite an accomplishment at that time. Often when we're discussing the idea of an axis, sometimes that axis becomes a line of symmetry. So a line of symmetry is kind of an imaginary line that you might strike down a building or across a city plan or a town plan, and if you were to fold that over, then it would match up and the two sides would kind of mirror each other. So bilateral symmetry says that there's a central line of symmetry or central axis point around which two of the halves, if put together, would be identical. Now this is the floor plan of Unity Temple by Frank Lloyd Wright. This was built in the early part of the 20th century in Oak Park, Illinois, where many Frank Lloyd Wright buildings are constructed, where he's from. And so you can imagine the line of symmetry in this plan is not down the middle, top to bottom. Because if you folded that over, if you folded the left side and the right side together, they would not match up. But if you drew an imaginary axis or line of symmetry from the left side of the screen to the right and folded the top and bottom halves together, then those would match up. So we would say that this plan has bilateral symmetry, because lateral means side and bi means two, so two sides match up about that axis or about that line of symmetry. Now it's interesting that Unity Temple is meant to be a place of reflection, and I don't know if you can tell, on the left hand side is the main sanctuary. There is a pulpit and kind of an area for an organ and choir, but many of the benches at Unity Temple are facing into the central part, and then there are kind of these rows of benches in the main floor of the auditorium, and there are these kind of seats that rise up on the sides. And so it's really kind of a centralized plan anyway, and it's meant to make people feel like they're kind of all together in this one unifying space. Here we look at Unity Temple from the street view, and if you were orienting yourself to the plan that was on the previous slide, then you'd be looking kind of from the bottom of the slide. And so, you know, here the left hand and right hand portions of the building are not symmetrical. You couldn't put those together, but the side that you're looking at and the side that is kind of facing the rear of this photograph, you could put those together and they would be symmetrical. Now it's not just the plan that has symmetry here. There are various elements that are symmetrical, like these columns, these kind of fluted, detailed columns. Those are symmetrical. You know, they have even numbers, so there's just 4 on the smaller portion of the building and 6 on this larger portion of the building. So if you were to strike a line of symmetry and look at the two sides, those would be symmetrical. So there are individual portions of the building that contain bilateral symmetry, and you see this idea of symmetry throughout. And it's kind of a unifying principle of the entire structure. And some of what you see is meant to be perceived as a sanctuary space. So, you know, it's quite monumental on the outside. You can't see in directly to the sanctuary from the outside, and the windows are placed high up so that that light comes in above you and filters down into the building. But it's meant to feel as if, you know, people are kind of contained within the building and protected from what's going on outside. When we look at the time that it was built, this was built between 1905 and 1908. This is quite early in Frank Lloyd Wright's career, but he is starting to experiment with architectural precedent, which means he is looking toward previous examples of classical architecture and putting his own spin on that, and also looking at monumental architecture and things that were meant to symbolize something greater than the people inside. And so you see reflections of previous examples of monumental and classical architecture with his own details and maybe some minimalization of some of the more filigreed or ornamental applications that some previous examples of classical architecture might have demonstrated. The next structure that we look at is the Great Stupa at Sanchi in India. And this is an example of radial symmetry. Now, when we look at bilateral symmetry, the implication is that there is a single line of symmetry or a single axis that you could strike across either the plan or section of a building, and the two halves would be symmetrical. In radial symmetry, it's not just the two halves, even though there is bilateral symmetry here in this building, where if you were to strike a line of symmetry right down the middle, the halves would be the same. But in radial symmetry, it means that you could strike more lines of symmetry than that, and different parts would be symmetrical as well. So this is a round structure, so you can imagine if there's a point in the center of this plan or the center of this building, and you started striking lines of symmetry radiating out from that central point, that several of the sides and several of the halves would start to match up. Now this is an interesting comparison to Teotihuacan because parts of the structure were built around the same time as Teotihuacan. So this was begun slightly earlier, around the 2nd century BC, but was continued to be constructed into the 2nd century AD. And it's interesting to see the comparison of these two cultures and how they used local elements, how they expressed elements of their culture and their construction techniques, and what they viewed as important in their buildings, but were occurring in disparate parts of the world, but at the very same time. As we look at the plan of this structure and the elevation, you can see that there are points at which if you struck lines of symmetry kind of going through the middle, as long as they were going through the middle, you could strike a line kind of going up and down, one going side to side, or even, you know, at 45-degree angles going through the center of the building one way and then diagonally the other way, and all of those sides would match up. So it has both bilateral symmetry and radial symmetry in the plan and the section of the building. So if you had a section cut of this or a cut going through the building, you could see that the sides would match up. This was commissioned by Ashoka the Great and is still the oldest stone structure currently in India. This was originally constructed as a Buddhist sanctuary, often referred to as a vihara, and the Buddha is or was constructed in the middle, and then the sanctuary or the structure is built around it. So originally it served as a religious site and a site of worship, so became a sacred space, and often people will say that you could move around the Buddha that was at the center, and so hence the round structure and the round plan, and it gains something from the idea of radial symmetry. The next ordering principle that we look at after symmetry is hierarchy, and there are several different types of hierarchy. When we think of hierarchy, it usually means objects in a series. The idea of hierarchy is pervasive in life today. I mean, you could say that there are hierarchies in government or businesses, or, you know, in graphics you see different things being more dominant than another. Typically we're talking about hierarchy as either object dominance or something else being more significant or in a certain order as compared to something else. So one idea of hierarchy is hierarchy by size. So that just simply means that one object or a part of an object is larger than the others and therefore becomes more dominant because of its size. Now this example that we're looking at here is the main cathedral in Florence, and it's often referred to as the Duomo or Il Duomo, and that means the dome, because the dome of this structure is so dominant that it is much larger than any other portion of the cathedral. But we also look at this because the Duomo and the cathedral itself is more dominant in the skyline and cityscape of Florence than any of the other buildings that are in the city. Now here on the left we're looking at the interior view of the dome, and you can see that it's overwhelming in its size, but also it's extremely detailed in the paintings and the construction of, the murals that you see inside. On the right hand side, this is a digital image of a cutaway of the construction of the dome, and on the exterior you can see the marble paneling. There are all these beautiful green and white marble panels, and that in itself is quite unique. And when we look at the dome in relation to other parts of the building, even though there's kind of a significant tower on the left hand side, the size and shape of the dome really overwhelms everything else that's going on in the structure. Here you see the cathedral at night lit up with the surrounding buildings of Florence in the background and kind of in the foreground, but its hierarchy is established by its dominance over other buildings and the size of other buildings in the city. So in Florence, Italy, this was constructed kind of in the later part of the 13th century, and it was originally designed as a Gothic church and was begun in 1296. So Arnolfo di Cambio is the original designer, but mostly this is attributed to Brunelleschi. So Filippo Brunelleschi is mostly known as the architect because he designed the dome, and the construction of the dome occurred under his watch, or kind of his design. And so the hierarchy is really established by both the dominance of the dome structure on the church and by the church itself as a symbol of Florence, as a symbol of the skyline or kind of cityscape of Florence. And you can see this from most parts of the city. And mostly it's what Florence is known for. It's the #1 attraction in Florence, among many other attractions in Florence, but this is mostly what people think of as a symbol of Florence, Italy, when you think of its most dominant feature. There are other forms of hierarchy. Another one is hierarchy by shape. So here in this graphic we see you don't have to have something as a larger size in order for it to be hierarchical. So hierarchy by shape says you have things of the same shape, and then if you have something a different shape, that in and of itself becomes noticed because you are kind of glossing over all the other shapes because they're the same, and then once one is different, it kind of pops out and jumps out at you. Now that could be by the shape itself, like with the example of the circle on the left, but you could also have something that's an identical shape, but by shifting its position it then becomes a different shape because it's different in relation to the others. And so this square that's on the lower right hand portion, you see that just by twisting it at a certain angle, that also jumps out at you. So graphically, if you kind of stand back and you look at these shapes, the two things that are going to jump out at you are the circle and the rotated square. So that hierarchy by shape, that can be done in several different ways, but it forms a type of dominance just by the shape that it takes on. Now we see this occurring several times in architecture. You see this in town plans or city plans, but certainly if you have a building and you want to create a hierarchy or establish a hierarchy, you can make something dominant just by even slightly altering the shape of elements in the building. Another type of hierarchy is hierarchy by placement. And hierarchy by placement says that you could have elements of all the same shape, all the same size. They could even be in the same position. So this square, kind of in the upper left, is not rotated at a different angle. It's not placed in a different orientation or a different position. But just by creating some space around it and by placing it further away from the rest of the elements, that creates a hierarchy or a form of dominance, and that isolation of the element makes you notice it. So sometimes when we are trying to maintain a focus on a certain element, you might establish kind of a void space around it or a zone around it where there are not other elements, and so that creates a sense of dominance by just that object being isolated or by itself. Another ordering principle that we look at is datum. And datum is an interesting concept because you can see datum lines or datum planes in lots of different things in life. So in the book, it uses the idea of music, like music on a page. So there are these lines that are established in music, the lines of a musical staff, and those remain constant. So those lines always stay the same, but there are notes that kind of jump around, and depending on the pattern or the rhythm of the music, those notes might be together or spaced at various points depending on the note they are around those lines. But the datum is the thing that remains constant, so the lines on the music remain the same and the notes jump around. Now that can be applied to architecture as well. So this idea of datum, it could be datum lines, it could be datum planes, and it could be datum volumes. You know, you could have chunks of objects or chunks of space that form datum points, or, you know, this idea of datum. But here we're looking at datum lines in a plan. So on the right hand side you see this town plan, and this is a grid plan, meaning all of the streets or all of the thoroughfares become planes that are intersecting each other, and it forms a grid. So actually that does not mean that every single building is the same. In fact, if you look at all of the individual walls, this is kind of a graphic depiction of what the walls are doing in these individual buildings. And this is a Roman colonial town called Timgad, and Timgad is in modern day Algeria in North Africa. But it really is a unique example of an orthogonal plan on a grid, and that was not, you know, typical for that time. And in the next slide we'll look at what the current state of this city looks like. It's a ruined city, but you can see the ordering system of the datum lines of that grid, and they're very strong. And when you look at even the central kind of gathering spaces, kind of at the bottom of the screen, like this central amphitheater and central kind of city hall or city plan, that still maintains that idea of the grid, and the grid is really strong throughout the entire town. Now, when you look at the ordering principle seen here, there are probably lots of different ordering principles that you can see. You can see axis lines, you can see lines of symmetry. There are even terminating elements in, you know, kind of that central top to bottom avenue, or that line with some columns on it that probably terminated into this central city building. But the datum of the lines of the grid are really the dominating feature. Now in Timgad you can see this is what it looks like now, and you know, the grid is extremely obvious. And so kind of on the left you can see a more dominant line of axis or dominant avenue that probably had columns along it. And it was commissioned by the Roman Emperor Trajan. So in the previous slide, and you can go back, but there was a gateway arch at the central area of the city, and it's known as Trajan's Arch. And that was in honor of Trajan, the Roman emperor. And this is also built around 100 BC. So you can imagine this and the great stupa at Sanchi and Teotihuacan all being built around the same time, all with entirely different civilizations, but you can start to see these ordering principles played out in civilizations that obviously didn't know what the others were doing, but you can see them using their local materials. You can see the construction techniques that were used here. And again, interesting to see what was occurring at the same time in different parts of the world. Some other ordering principles that we look at are rhythm and repetition. Now, rhythm and repetition are related to one another. When we talk about rhythm, we're talking about how principles or elements that are either different or similar or even the same tend to get repeated and then form kind of a series of elements or a series of points about which a design of a building or anything else is created. Now we're looking at a cutaway of a nautilus shell, and the nautilus shell is a good example of this, and you can see elements of rhythm and repetition a lot in nature. And even though in the nautilus shell, as we're looking at these individual fins or these individual compartments of the shell, they are not the same size, right? They're all getting larger as they radiate out from that central point of the shell. But they're so similar, and their features and details and curvature are similar, and their spacings, even though it starts to get bigger, it creates this rhythm where it's almost a predictable spacing and rhythm. And that's where we start to get things like the golden section and other ordering principles, because there's almost a mathematical algorithm that's created by starting in the central point and then those features becoming increasingly larger and the space between them becoming increasingly larger, and that repetition becomes the rhythm that is created about either a central point in this case, or maybe along an axis, or throughout a facade of a building. And you see this played out in all different kinds of ways in architecture. So it could be through the size of an element, it could be through the shape of various elements, or individual detail characteristics. When we talk about detail characteristics, it doesn't necessarily have to be on every single object, but here in the nautilus shell, it might be that individual tiny ridge or that tiny rib in the middle. We're seeing it cut through here, but these little white chunks on each of the compartments of the nautilus shell, even something like that you might consider a detail characteristic. And so as you see that repeated over and over, you could almost draw an imaginary line through those. And then as you curve that line around, you could imagine that the next one, you could predict where that was going to be located and in what part of the shell it would occur. Now the shape of this, you could have this rounded shape. Because there's a rhythm, it's predictable, and visually it's predictable. So, you're not going to come around in the shell and have one of these ribs or one of these compartments curve the other way, because that's just not the pattern that's established. It's not the rhythm of the elements. And so the repetition, they don't have to be identical to create a rhythm. They could be, but they don't have to be, but they're typically some kind of ordering element or ordering system that is occurring, whether it's in the size, the shape, or detail characteristic of an architectural element. Now we see this in architecture a lot. So it could be with a group of buildings, it could be within a building itself. This is in San Francisco, and this is looking at some of the Victorian houses surrounding Alamo Square, and these are really kind of an iconic representation of San Francisco architecture. Now, if you look at these buildings, these houses, they're not all the same color, and they're not all exactly the same. Some of them appear to be somewhat identical, but as you look closer, some have arched doorways, some have a little gable on top, so they're not exactly identical. But the rhythm is established by at least the majority of elements repeating, and they're not even repeating along an identical line, they're sloping down on a hill, but because they're spaced the same distance apart, there's a definite rhythm and pattern that's established in those houses, and as a group you can see that rhythm occurring, and because there's such a rhythm, you almost convince yourself that they are identical, even though if you start to look closer, there are many elements that are similar but different, but there's enough repetition of sameness that's occurring that it definitely establishes a rhythm with all of the buildings. Now we see this in several architectural elements. This is looking at a temple in India, and this is actually a series of temples. This is a temple complex. It's a Dilwara temple complex, and these are Jain temples in India. Now, the idea of rhythm and repetition is seen throughout this complex, and it's seen by the repetition of various elements on individual temples. So you could pick out lots of individual architectural pieces that are repeating and establish a rhythm. So there are these kind of columnar pieces, these columns that keep repeating. There are carvings that keep repeating. The entrance archways step back from each other but are the same columns and arches, and those occur at several levels, but those keep repeating. And so there's a rhythm of architectural elements that's established by the repetition of things that are going on. Now, this isn't just one isolated temple. So there are 5 main temples, and as we start to look at these, they're not even established in a ordered, bilateral symmetrical pattern. They're kind of offset from one another, but because there are so many repeating elements in these temples, that you can tell that they're definitely related to one another. Some even kind of touch each other at the corners, and then there's space between some of the others. But these Dilwara temples are known for their repetitive elements and their rhythm that's established with the architecture. Some other elements that we see inside, it's not just the exterior that is repeating, and not just the exterior that has repeating elements. You see these very elaborate, intricate carvings, and they're extremely elaborate in their use of marble. So marble is the main building material, and they're stunning because of how much marble is used and these intricate carvings. So you see repetition like in a radial way around domed structures. You see carvings supporting those domes and columns, so those elements repeat. Some of the carvings themselves repeat and create a rhythm. This was built between the 11th and 13th centuries AD, and if you look at the plan of these temples, they're not all exactly the same size. They're similar, but again, because they have all of these repeating elements and the rhythm that occurs with those repetitive elements, you can tell that they're related. And this is located at Mount Abu, India. Transformation is another example of an ordering principle that we see in architecture. And you can see this in all different buildings in lots of different ways, both in classical architecture and modern architecture. There's basically a single element that you might have, and it's kind of like variations on a theme. So if we were looking at this model, this is kind of a graphic interpretation of transformation, where you would have these tall cylindrical, well, not cylindrical, but these square kind of tubes, right? And then you say, okay, some of them become curvy and taller or shorter than one another, and then there are groups that become smaller and narrower, but you can start to see unifying parts of what was originally the same thing. And so transformation basically says, I'm going to take an architectural element and start to modify different values or aspects of that particular item, and then group those or show them in a certain way that makes the user see that you have transformed that item and you have interpreted it or transformed it in some way that creates almost a unifying whole of architectural objects.